This conference will now be recorded.
Very good evening, students. Today we'll be picking up numerical problems from modern physics part, where we will be covering photoelectric effects, semiconductor, atoms, nuclei, etc. So these are all questions from previous year's JEE paper. So this particular question was asked in JEE main 2013. Okay, so let us try to solve this problem. Anode voltage of a photo cell is kept fixed. Anode voltage is kept fixed. The wavelength of the light falling on the cathode is gradually changed. The plate current of the photo cell varies as follows. Which of the four options will be correct? You have to find out that. So we know, you might be remembering the photoelectric effect, the photo cell, where we will have cathode, photosensitive cathode. Upon incident, upon illuminating that cathode, electrons will be emitted. It is actually from photoelectric effect. So when see, you have cathode plate here, where the radiation is coming, it happens actually in a evacuated chamber. Okay, so here the light is falling and there is obviously anode. So when the voltage between anode and cathode, this is cathode and this is anode, this is fixed. What is that? Actually, the electrons acceleration due to this voltage is fixed always. Now see, this wavelength of this of the incident photon, see how does this depends on the energy. Energy is equal to hc by lambda, and you know, how would current vary with lambda? It is you know, like if you have a photon of energy h nu, okay, or hc by lambda, one photon can knock out only one electron. Okay, only one electron it could be knocked. Okay, if you want to know the variation of photocurrent, that means you need to know how the emission of electron depends on the energy. First of all, the energy of the incident photon, and you know, current, photocurrent directly dependent on intensity of the light. Intensity of the light, that means, you know, you have greater intensity, means you have greater number of photons per unit area, then you can knock out many number of electrons. Okay, as one electron can knock out only one photon can knock out only one electron. Okay, so if your intensity is greater, then you get more number of electrons, and you get more and more photocurrent. right? Now, how is this intensity depends on? Intensity depends on energy. This intensity depends on energy directly. Okay, intensity depends on energy directly. Now energy again depends on lambda. So we can imply that intensity of the incident light directly proportional to 1 over lambda. So if the intensity is decreasing exponentially, okay, sorry, inversely, so if this is inversely proportional to lambda, then the current, when lambda will be increasing, intensity decreases. If intensity decreases, then photocurrent decreases. Okay, so out of this four, this could be the best uh, thing, like best or the correct answer for this question. So intensity actually depends on wavelength inversely. Therefore, the current also will depend on the wavelength of the incident photon inversely. Okay, so this is the answer for this question. We'll move on to the second question. This is from semiconductor part. It is very interesting, and obviously, yeah, so since it is a modern physics part, we may need some other concepts also. So here, look, a red LED emits 0.1 watt uniformly around it. So you know, so you have LED like this. So this is emitting light uniformly, like it is kind of a point source, so light actually spread out sphere, okay, like this from the center, like keeping this LED at the center. Now the amplitude of the electric field of the light emitted by this LED, the amplitude of the electric field of the light at a distance of 1 meter from the diode. So this is the distance and this is the diode. So actually, suppose this is the diode. Actually, what you should do, you should just take this distance to be the radius of the sphere, okay, and then the energy, light energy spreads like over this surface of the like from the surface of the sphere of radius of this 1 meter distance. Okay, this is diode. Now what is the intensity here? We have a relationship between power and intensity, and you might be thinking why I'm writing about intensity, because intensity has a relationship with the electric field directly. So intensity is equal to the power divided by the area of this sphere, okay, 4 pi surface area of the sphere, this. So this is the power, this is, okay, so this is intensity. And how intensity is related to the energy, it is equal to half epsilon 0 E square c. This is the intensity. This is the relationship with intensity and electric field. So from here we can write electric field is equal to 2 into intensity divided by epsilon 0 E square and c. Sorry, E square was taken left hand side. So here 2 into, see this intensity is let me write P by 4 pi epsilon naught. Okay, so from here we have written 2 into intensity is this P by 4 pi, R square will be there here. Okay, so this is the relationship. Now if we do one thing, if we calculate E, what is E? With 2 into 0.1, that is the power watt, divided by 4 pi epsilon naught into 1 meter distance. So we have to take that as the radius of the sphere. So from here what you can do, once we the key point is here that you have to know the relationship between intensity and the electric field. So 1 by 4 pi epsilon naught means 9 into 10 to the power 9. So this will 4 pi epsilon naught this. Okay, there would be, okay, so this C I have left out, so there will be C here. C means 3 into 10 to the power 8 meter per second. So it would give you actually 3 3, so it will give you 6. This is not E, this is square still. Okay, now E is equal to what? E will be then square root of 6, and this would give you 2.4 volt per meter. Okay, so I hope you guys understood this. See here, intensity is equal to power by area. Area means the distance you see, that has to be taken as the radius. Okay, so P by 4 pi R square, and intensity is related to electric field as half epsilon naught E square into C. Okay, like this, and from here we can find out what is E square, and thus we can find out what is the magnitude or amplitude of the electric field. So it turns out to be 2.45 volt per meter. Now we'll go to the third question. So this question is again important question. Let us solve this. So this question says that the radius of the orbit of an electron in a hydrogen atom is. the radius of orbit of an electron in hydrogen, in a hydrogen like atom, not hydrogen, in a hydrogen like atom. That means, see, in case of hydrogen, z is equal to 1, but in case of hydrogen like atom, it is other than 1, z is equal to 2, 3, etc. Okay, z is equal to, z not equal to 1, it is greater than 1. So that is given here, 4.5a0, that is the radius of the orbit of an electron in hydrogen like atom. A0 is the Bohr radius. Its total angular momentum is given. Sorry, orbital angular momentum, not total. Orbital angular momentum is given for that particular orbit. And it is given as, given that h is equal to Planck constant and r is the Rydberg constant. So now, what are the possible wavelength when the atom de-excites? So you have to find out possible wavelength. Okay, so look here, first of all, uh, radius, let me write, radius of a hydrogen like, let me write as H like atom, in short, H like atom is given by A is equal to A0 n square by Z. Okay, A0, where A0 is the Bohr radius. So here in this case, what is given? The radius of the hydrogen like atom is given, this is equal to 4.5a0. So from here, we can actually get a relationship between n square by z and okay, this we can write. Let us give, this is 4.5, this, let us give this as equation number 1. Now another hint is given is that the orbital angular momentum in that orbit, see here the orbit I cannot decide unless I know, we cannot put the value of n, and z also we cannot put any value unless we know what is this atomic number. So look, according to both quantum condition, the orbital angular moment will be nh by 2 pi, and that is equal to 3h by 2 pi. This goes, so n becomes 3. That means the electron is there in the third orbit of the respective atom. Now we have 4.5 a0 is equal to a0 n square by z. A0 can be cancelled out, and see, n we know, n we have got from the previous slide, n square by 4.5. So n is 3, so it will be 9. So from here we can write Z is equal to 2. Now look, if I know the location or the principal quantum number in small n, obviously here, if we know the atomic number and in which orbit it is orbiting, can we find out the energy? Answer is yes. Sorry, energy you can find out, and energy or we can, yes, we can find out the energy in terms of Rydberg constant, etc. So what you can write, so we have an electron in the n is equal to third state. You have n is equal to second and n is equal to 3 state here. Okay, first state or ground state. This is nothing but ground state. Your electron is here, so it can be de-excited through two ways. Either in 3 is equal to, that means 3 to 2, or 3 to 1. Okay, n is equal to 3 to n is equal to 1. These two possible uh, de-excitation scheme is possible, like are possible. Then we can write down expression for 1 by lambda square is equal to r z square whole into n final square. Okay, this is the thing. Now see, final is for first, let us suppose lambda 1. Lambda 1, 1 by lambda 1 square is equal to r, let it be z is 3, sorry, z2 square, and this is 1, final square is 1, suppose this is 1 and this is 3 square, so this is 2, we'll write already, so this 4 into this is 1 square, so this will be 8 by 9. Okay, okay, so this is the, so lambda 1 9 by 32 hour. So this is the lambda wavelength due to the transition from 3 to 1 state. Okay, now we have another possibility, this one we'll calculate the wavelength for that also. So when n is equal to 3 to n is equal to 2, this, so in this case 1 by lambda 2 square so nf we know 2 and 1 we know, so this is rz square, anyway I'll write later, this let me put these values. N1 square. This is 1 itself. This is 4. I'm sorry, this initial will be 3. Initial 3, and I have written, I think, yeah, these are little wrong. This is final and this is initial. So final is 4 and initial is 9 here. So here actually you'll get 5 by 36 R. Okay, then I'm sorry, these are actually not square. I have written by mistake, this is not square. Okay, 1 by lambda, just 1 by lambda. Here also this is 1 by lambda. So this will give you lambda equal to, so z square also was there, right? So this will be here 4 multiplied. So here 4 multiplied. So lambda will be 9 by 5 r down. Here it is 9 by 32 r, and lambda 2 will be 9 by 5 r. Okay, 9 by 5 r. So these are two wavelengths possible. Look here. So what are that? So 9 by 32 we have got one, and 9 by 5 r we have got. 9 by 32 r and 9 by 5 r. So these two wavelengths are wavelengths will be obtained in the de-excitation process. Now we'll take up few more problems. I'll just write down the problem. Let us take on problem from radioactivity. So question number 4. The half-life of the half-life AT is 100 microsecond. The time taken for the activity of the sample to decay to 1/16 of its initial value. So what is the question? The value, not the value, uh, the half-life of AT215 is 100 microsecond. The time taken for the activity of the sample is to decay 1/16 of its initial value. The times are given as 400 microsecond, or option B is 63 microsecond, 30 option, and D is 300 microsecond. Okay, so you have to find out the answer, the right answer for this. You know, activity and decay of original number, they vary. So activity, actually we can write A is equal to A0 e to the power lambda minus lambda t. So this is how it varies, okay, with time. Again, we know t half is equal to n2 by lambda. Okay, so if we want to get the time, let us first put the lambda, because lambda is not given, so you can put the lambda from here to here, and look here, from here I'll just keep in bracket. What we can write from here is that a by a0, this is nothing but 1/6 e to the power lambda is equal to that lambda t particular time. And see, lambda here put as, sorry, ln t by t half. Okay, 1/6. So all right, 1/6 e to the power can right. Okay, lambda in place of lambda t up by ln t is there. Okay, so in place of lambda I am writing, then it will be in the numerator itself here. So lambda will be by t half n to, okay, that's what 1/16 1/6 is equal to e to the power minus t. I have to find out, and this t half, t 2 and divided again. Okay, we have to find this. So look, minus ln2 100 microsecond, okay, into t over here is equal to 1/16. Okay, so from both sides, if we take for time, if we solve for time, what would be obtained? We would obtain t is equal to 400 microsecond. Okay, you have to solve this to get t. Both sides, what we can do, we can take anti-log. Let me just try out. So this is ln2 by 100 microsecond into t. So this is ln 1 minus ln 16. ln 1 is 0 actually. So from here, look what we can further write. So this will be 0, 100 microsecond into L16 by ln2. That means 100 microsecond, okay, ln2. See, this we can actually simplify a bit. So ln 2 to the power 4, 2, 2, 2, and 2. 2 to 4, 4 to 8, 8 to 16 divided by ln2. So this 4 would come near, and this ln2 over ln2 will cancel each other. Okay, that's how you would get. Okay, so 400 microsecond is the answer. Now we'll take one last problem. The energy of a photon, let us just write the problem here. Question number 5. The energy of a photon is equal to the kinetic energy. I'm writing in short, kinetic energy of a proton, The energy of the photon is E. The energy of the photon is E. Let lambda1 be the de Broglie wavelength of the proton. Let lambda1 be the de Broglie wavelength of the proton, and L2 be the wavelength photon. The ratio of the ratio lambda 1 by lambda 2 is proportional to the options are is 0, option B is per half, C it is per minus 1, and last one option D is it is per minus 2, option D is 2. Repeat the of a photon is equal to the energy. The energy of a photon is equal to the kinetic energy of a proton. The energy of the photon is E. Let uh, let the lambda 1 be the de Broglie wavelength of the proton and lambda to be the wavelength of the photon. See, if the energy of the photon is E, this can be written as hc by lambda. Okay, let us write that as lambda 2. Okay, and de Broglie wavelength, we know this is proton kinetic energy. So kinetic energy of the proton will be written as if this is the kinetic energy, E is the kinetic energy, then what will be the momentum? Linear momentum is so P square by 2m is equal to E kinetic energy. So it will be square of 2m into E. Okay. Now de Broglie wavelength lambda 2 will be H by P. P is over M. Okay, this is if you now do you get lambda by lambda by lambda lambda 1 lambda length wavelength of lambda 1 is the wavelength of the this is a proton. This is lambda 1 length of the proton is by P by P is H by lambda and lambda then see lambda 2 was H by lambda E was H by lambda So C by lambda. So lambda 2 will be so HC, and here it is E. A will be a factor goes up anyway, like a constant factor is 1 by root of r. I have put in the minus half. It's have 1 as so the square root then lambda 2 is directly produced half. Is there any option? The answer for this question. Maybe we can take one more problem. Let us take one more problem before we finish. Question number 6. This is from again nuclear physics. A nucleus with mass number mass number 220 initially at rest initially at rest emits an alpha particle. If the Q value of the reaction is 5.5 MeV, calculate the kinetic energy of the the kinetic energy of the alpha particle. Okay, here the options are 4 MeV, then option B 5.4 MeV, option C is 5.6 MeV. Okay, 6.5. So rate the one. Let us a nucleus with mass number 220 initially at rest emits an alpha particle. The Q value of the reaction is given. So Q value is given as this. Okay, and mass number is 220. Okay, 220. Okay, now the kinetic energy of that means is alpha. Okay, let us So with to solve see a nucleus with mass number 220 initially at rest with actually suppose there was let us take that as some x, okay, 20 mass number. To when alpha particle emit, let us say the mass number would be equal. Now what is total is energy, suppose the energy, this energy of the energy of not recoil, I'm sorry. Yeah, so this will have some acceleration and alpha particle also will have some acceleration. So due to that it has some energy, and obviously this nucleus also will have some recoil energy. Okay, so these energies are there, and if we see the total mass to be m alpha plus m oy, right, m oy. So we look here, the from the conservation, from conservation, from law of conservation of linear momentum, we have to find out the kinetic energy. So if we find out the velocity somehow, or let us find out the momentum itself, momentum of the alpha particle, then it will be easy to find out the energy, kinetic energy. So from conservation law, we get initially the nucleus has some momentum, zero momentum, right? This is zero. That is equal to the momentum of alpha particle, and this is recoil. That means it will be in the opposite direction. So this will have some momentum. Therefore, you know, the momentum of alpha particle will be momentum equal momentum of this nucleus itself. Okay, so if we now if we want to find out, see this is alpha particle, this is the nucleus. So again, total energy we had got like this, right? Total E is equal to E alpha plus this Uy. Okay, so what we can write, this M alpha into E alpha is equal to My and Ey. Okay, so from here we will be able to find out E alpha to be this. Okay, so this EY, which is given in the form of Q value. Okay, okay, let's see here. E alpha is to MO divided total by total mass Q value. Okay, this is how it will come. Add Q value this and Q this 5 MeV. So 5.5. This would give you 5.4. Okay, so we'll stop it here with this. We'll meet again tomorrow. So thank you for your patience. Bye for today.